Your assignment number 1 has been released yesterday. It will be due in about 2 weeks, but I would suggest try to really get started and also complete it as soon as you can. Your programming test number 1 is going to be somehow based on assignment number 1. Okay, so just make sure you finish that in time. It's quite a nice exercise for you to really experience the whole workflow, like how we did the tree rotation, checking balance, etc. Everything has to be implemented precisely. I think it also will push you to really your understanding, hopefully, to another level. Okay, so that's the intention. But get started, and then you can ask me any questions during the office hour. So tomorrow, tutorial number 5, I definitely want to do mathematical induction. Maybe I can at least do 2 examples together with you, one on the graph, one on the tree, and also we can also do the deletion cases. While the assignment is not really about deleting nodes from binary search tree, to keep it balanced. But I think, just a review about the tri-node restructuring step can actually help. So I'll do the complicated case together with you for tomorrow. Okay. And I might just, if time permits, I'm hoping, I really try to get started in time. Hopefully the projector, everything is going to work well. So I'll give you guys maybe some high-level tips about the assignment number 1. I don't want to give too many because it's really the fun part about the assignment. You really want to think about what we learned in the lecture using visualization and how you can convert that into executable code. It's a very important skill, especially being a software engineer. It's a very non-disposable, right? You definitely want to make sure you can do it. Okay. Any questions in general? Alrighty. Okay, good. So today, let me give a little bit look ahead. We're going to cover more terms about graph. I think after today, most of the terms, the basic terms about graph will be done. However, today could be very confusing. There are so many terms we have to learn about, but as I promised, I'm going to give you a table to summarize all the terms, but you're just going to hang on there, right? So let's now start it. We'll go kind of smoothly. So we'll start with something gentle. Okay. Just before that, let's look at what we cover on Monday. On Monday, we basically spent about half of the time talking about mathematical induction. So this will be the principle you want to do base cases. Oh, sorry, that's not mathematical induction. Beg your pardon. Right here. All right, so you got to do base cases, and also you got to work on the inductive hypothesis, which may or may not be given to you in general. You may have to figure that out yourself based on the property you want to prove. And also, you want to somehow use the mathematical induction to prove something that's strictly bigger than what you assume. That's really the roadmap. Another important thing you want to also get used to is this. Whenever you're given some property, right? The property itself may or may not hold universally on any graph that we're assuming. So today we're going to see some example. There will be, for example, 3 to 4 properties. Somehow, intentionally, one of the property is not exactly true always. Maybe I can pause. Maybe once we get to that point, I can pause for a moment and let you guys to think about which one may not be provable, right? Maybe for that one there, you have to show some counter example. But just remember, whenever you give a property, don't take it for granted just yet. So it could be that you have to either prove it using induction, or you have to disprove it using some counter example or witness, right? Just remember that. And then talk about a graph being complete, right? And then there's a mathematical induction itself. I would say this one here is really nice. It's not that complicated, but it does show many good ingredients about how you can use induction. We're going to see different examples tomorrow. And I think I do have more. So either we can definitely do some tomorrow, and then we can even do one more or 2 more, maybe before the reading week. So you really get comfortable with induction. And we talk about path versus cycles. You just got to make sure you understand the difference between path and also simple path, and also the difference between cycle and simple cycle. Right? Just remember, for simple cycle, if you take the beginning and the end, of course, they are the same, which is why it makes it a cycle. However, what's in the middle here is a simple path. That's why it's a simple cycle. Right? Just remember the definition. Okay? And also, you should be able to either work out some example by yourself from scratch, or if I give you some example, I want you to judge similar. Okay? And that's just more clarification about cycles being simple or not simple. Okay, so these are what we're going to go over today. Question?
Would a graph with only one node have one cycle?
You wouldn't say that though, right? That's the question was, if I understood correctly. Let's say you got one node, let's say X. So in here, in order for Well, in order for the graph to be cyclic, that means there should be a path which will start with certain node, and the only choice you have is x. And then it should end with also x. But in this case, we don't have such path. We don't. So you don't say this is actually cyclic. You don't say that, right? So since I'm writing that down, why don't I put it here? Okay? It's a good question, right? So think about right here. So let's say we talk about a one-noded graph. And then there will be just one node without any edge. Of course, the only possibility you can have an edge, it would be have to have a self-loop, which will make the graph not simple, right? So let's say that's the only node we have without any edges. So we'll say that this graph, the graph is acyclic, which means there's no cycle. You can think about because x to x is not a valid edge. All right, good. All right, and then, so today we're gonna actually move on. We actually only covered subgraph last time, so we got lots to do right here, right? We're gonna talk about all these in sequence, okay? And then subgraphs, that's what we spoke about. Subgraphs is really simple idea. You basically just take the subset of both the vertices and also the edges. Just take subset, right? Doesn't need to be exactly equal to the original vertices or the original edges. Any questions about subgraph? All right, let's make things a little bit more complicated. Let's say, what if a graph is spanning? Okay, so that's the next one we're going to talk about. Okay, so we talk about spanning subgraph. Okay, first of all, what does it really mean? Okay, the slide. I will try to occasionally go back to the slides, but it's kind of tedious to just read it off. I'll try to do just an example and write some definition on the notes. But we're gonna start today's lecture from slide number 18, right? Just remember that's the starting point for your study. Okay. So what's really a spanning subgraph? First of all, it's a subgraph, but it's a special one. So spanning subgraph by definition, right? Spanning subgraph. It's a subgraph, for sure, that, well, let me put it a little bit more informally, that spans, which means covers all of the vertices through all vertices. For example, let's say given this graph G, what will be the simplest spanning subgraph I can create? The simplest would be I just let the subgraph to have vertices only without any edges. That'll be the simplest one, right? I'm not even considering edges. So for example, I can simply do, let's say the subgraph is simply A, B, C, D, E, and F. So you can think about right here, I simply disregard all the edges. So there could be one confusing part, which I just realized when I went through the lecture today. So whenever I'm trying to say, given this particular graph, let's think about some subgraph. So the way I will create a subgraph is I simply highlight those parts that should be taken for the subgraph. So for example, in this case, when I say I highlight A, B, C, D, E, F, that means all the edges are disregarded, right? So just in case I forgot to put it explicitly, you should really understand, okay? So what I'm saying here is the subgraph is going to disregard all the edges right here, right? So all the edges are simply taken out. That's how we create this subgraph. So this subgraph over here has only 1, 2, 3, 4, 5, 6 isolated vertices without any edges. So it's a subgraph. So this is at the same time also spanning because that covers all the vertices in the original graph. Okay? So now let's formulate this condition here. So if I have a subgraph, let's call that G prime. Right? And then it will be V prime and also E prime. We'll say that it is a spanning subgraph of G, which is V and also E, right? So now we do have two reference points to really compare. So now what will be the precise condition? In order to be spanning, we only care about vertices. We got to make sure all the vertices are covered. Okay? So if and only if V prime equals V, right? So you can think about V prime is right here. And also the V is from the original graph. That's all we care. Edges, doesn't matter. You can take all the edges, you can take no edges. Right? I'm just doing one extreme case right here. And E prime subset E. All right, so that's a formal definition. Also, you get the intuition as well. In order to be a spanning subgraph, you just got to make sure you cover all the vertices. All right? And also, I want to give you guys one look ahead as well. As we go over the lecture today, you will see several criteria about judging the property of the graph. Okay? So what we learned earlier, something about, okay, so we talk about like properties of subgraph or just a graph. So there will be actually several properties we're going to go over. So one is undirected, right? That's pretty much the assumption we are making. So we just have no directions for the edges, just for simplicity, right? When we define the trees and also forests by definition, they should be undirected as well. So for now, just assume we have no directions just yet. Okay? Undirected is one thing, and also cyclic or not. Cyclic or acyclic. And then the one we just learned, spanning or not. Which means does it really cover all the vertices? Okay, next one. Is it connected? Right, so these are pretty much independent somehow, independent properties you want to know individually. And then, of course, there will be some cases where they can somehow intersect, which we'll see as well in some properties. Okay? So these are the properties to really keep in mind. And let's go back. Okay? Let's just see a little bit more example here. Okay, let's see. Okay, even though I haven't really introduced about, we have already seen cyclic and also spanning so far. We haven't really talked about connected, but connected is pretty straightforward. A graph will be connected if somehow every pair of two nodes can be connected somehow. Well, I'll show you. Okay, but let's just see some example here, so you will see. I just want to give you a different flavor. I'm going to give you 4 examples here. All of them will be a spanning subgraph. However, given that they're spanning, I want to see whether it can be cyclic or acyclic, or should be connected or not connected. So these are some independent factors that might intervene. Okay? Okay, let's start with the first one. So I got G1. Okay? And for the first one, I'm just going to write it out explicitly. Given that it has to be a spanning subgraph, that means all the vertices should be included. So we got A, B, C, D, E, F. Right? So what we got is we got A, B, C, D, E, and F. Okay, of course, this one here is exactly equal to V. All right, that's going to be the first time I'll write it. Later on, I'll just put a capital V so you will know what I mean. Okay? Now, let's play with the edges. The vertices are pretty much fixed because we're only talking about spanning subgraph. Out of the spanning subgraph, we talk about different other properties. Okay? Just to start with, let's think about some graph that's not really connected. Okay? Let's go for one extreme case. Let's say there's no edges, which is like this. So why is this graph not connected? For example, pick any two nodes, A and E. There is no path. For example, there's no edge in between them because we already disregard this edge, right? So if you pick, as long as you can find at least one pair of vertices that has no edge between them. In that way, you can say that the graph is not connected. All right? And another one. Okay, I'm going to put capital V here. Okay, let me just put it here. So capital V, and then for edges, let's put N, O, and P. okay? Maybe without polluting the diagram, let's use temporarily, okay? So let's say we still got all these vertices in order to be spanning. And I'm only taking M and also O and also P. So that's a subgraph. First of all, it's spanning. All the vertices are covered. However, it is not connected. Can anybody justify? In order to justify, you got to give me one pair of vertices where they just cannot get to each other somehow. C and D, for example, right? You can see C here and D here. It's simply not possible to go from C to D. Similarly, you cannot get from A to C. Also not possible. All right, so we're okay? Or you guys are somehow confused? Okay? Maybe for this one here, I'll just draw it out, right? I can see some confused faces, right? Which I'm not happy about, okay? So let's see here. Let's say we still got A, B, C, D, E, and F, right? So these are the spanning, okay? And then we only got N, O, and P. N, O, and P. So M here, and also we got O here, and also P here, right? So this whole subgraph over here is not connected because if you choose, you can see C here is isolated. It's simply not possible from C to get to any of the nodes. And also D here is also being isolated. You just cannot go from D to anywhere else, right? It's not connected, right? Intuitively, it's very simple. But later on, we're going to see how we can check automatically, algorithmically, to see if the graph is connected, right? All right, so these two are spanning but not connected. These two. So we got spanning but not connected. Okay, that's the first category of example. Let's see another one here. Let's see something that's spanning connected. However, it has a cycle. Okay. Let's say without a cycle first. Okay, that's kind of in the order in my notes. Okay. So let's say number 3. G3, we still got all the vertices. Okay? And we're going to make sure this graph now, we're going to, a subgraph, is going to be connected, but it is acyclic. So what I'll do is N, O, P, S, R, and also Q. Okay, right here. All right, let's see this one here. So we still got all the vertices covered right here. And let's now try to see how the edges should be connected. First of all, we got N, and then we got O, and then we got P, and then we got S, and then we got R, and then we got Q. All right, so that's a subgraph. Okay, I'll pause here. All right. First of all, are you convinced this is connected? Basically, so maybe later on when you study, you can take a screenshot. So that's exactly a subgraph, right, later on. So this one here, you can choose any pair of two vertices in the graph. There's always a path between them. You can double check, okay? Is this cyclic or acyclic? Is there any cycle you can see? Indeed, right? For example, you can see here, 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 here. It's a cycle, right? Awesome, right? So this first example here shows to you this one here is actually spanning, connected, but it has a cycle. Any questions? Okay. Number 4. Let's have another one that's spanning, connected, but no cycle. Well, obviously, if you want to reduce the cycle, well, if you eliminate the cycle, you can take out some edges, but you got to be still connected. So G4, still all the vertices, and then I'm going to put N, O, P, S, and R. Basically, I simply took out the Q from the earlier subgraph. That's what I did. Okay, let's take a look. I still got all the vertices right here, and then I got N, I got O, and then I got P, and then S, and then R. Number one, spanning all the vertices. Number two, connected, because between any pair of two vertices, there's a path. Number three, there's no cycle, right? As you can see, it's completely okay. Okay. In this particular case, number four, I can make a look ahead notes, okay? So this one here is spanning, connected, also acyclic. This is only a look ahead, okay? This particular kind of a subgraph with all these three properties is called a spanning tree, okay? That's something we'll see also later. And later on, in the almost the last bit of the course, after reading week, we're going to see how can you identify a spanning tree that's the minimum. Okay, that's something we'll see as well. Okay, we're going to learn some useful stuff from there. All right, when we got all these three properties satisfied, it is a spanning tree. And we'll talk about spanning tree as well in a moment. Okay, spanning tree. And whenever you got a spanning tree, again, a look ahead. Did you notice that? Well, I guess not. How many vertices do we have? 5. 1, 2, 3, 4, 5, 6, right? 6, okay? That, I'm pretty sure you can count that. How many edges do we have? 5. So, in this case, the number of vertices, beg your pardon. The number of edges is exactly equal to the number of vertices minus 1. This is a universal property for any spanning tree. And that's something we will have to prove by mathematical induction. And that's something I'll do tomorrow in the tutorial. It's not difficult to prove, okay? Okay, just remember, whenever you got a spanning tree, this particular properties that will link between the number of edges and the number of vertices will always hold, always, okay? It's a property that's just there, okay? Spanning tree, right here. It's already much information here, right? So, but you know, you just gotta get exposed to everything here today, and then you just gotta study over the weekend, right? Hopefully you'll get better. Anything you want me to clarify? Good. Okay, let's now move on. Just one more. So this will be an easy, quick clarification about subgraph and spanning subgraph. Okay? So when I say formulate condition, maybe by using subset, proper subset, you know, like relations, you know, kind of you saw in the math review. Let's say we have a graph, G prime. So let's say this G prime here is a subgraph. And in order to be a subgraph, we know that, let's write down right away. We know that V prime over here should be a subset of V. And also E prime should be a subset of E, right? Subgraph. However, right now we say that this subgraph at the same time is also but it's not a spanning subgraph. So it's a subgraph, but at the same time it's not a spanning subgraph. What should we change about the relation here? All right, so at least understand the question, right? Diego, go ahead.
If we change that V prime is a proper subset of V, then we will have a subgraph that is not a spanning.
Exactly, because proper subset tells you that it should be strictly smaller for the vertices, right? So that means it cannot be spanning. All right, that's good, okay. So let's now just try, all right? For example, I'll just draw one. So let's say we got A, B, C, E, and D. And then we got, let's say, as many edges as you like. However, we left out F, so it's not spanning, right? So this will be just one example where it's a subgraph, but it's not spanning. Another way to really visualize this is to see the proper subset idea. Okay, that's something we also did earlier when we talked about big O. But now we can use the same idea to formulate. Okay, so think about in this way. This will be the set of all spanning subgraph of G, where V prime should be exactly equal to V, right? And then it is contained within another family right here. And another strictly bigger. So you can think about spanning is just more like a specialization property. So that one there, it will be a subgraph of G. And for subgraph of G, we know that it's V prime is subset of V. So what we're saying now is there is certain graph, like what we are describing here, is a subgraph, but it's not a spanning subgraph. Where should we identify it in the diagram? It's not here, but it's here. So it's a subgraph, but it's not a spanning subgraph, which means this will be true, but this is not true. Okay? So thinking right here, so this is a subgraph that's not spanning. And if you want to see a little bit of derivation, so what we have is, first of all, it's a subgraph. So subset must be true, but at the same time, it's also not equal. So this whole thing here is equivalent to, by saying, by definition, V prime is a proper subset of V. All right? That's like what Diego said. I just want to make it more explicit. All right, question? Diego.
Do you mind reminding us again of the actual definition of a graph? Because I'm a bit confused on how something can be called a graph if it's just a bunch of vertices with no edges.
Yeah, okay, of course, the way we formulate a graph is by using like a pair. So we got a pair of vertices, and also the first component in the pair is a set of vertices. And the second component there is a set of edges. That's really a graph. One thing we wouldn't allow is to have a graph with edges only, because by the very definition, edges must have the n vertices, right? So yeah, so the simplest graph you might have is like an empty graph, right? And also the next one, you may have simply, let's say, an isolated vertex. That's just kind of like a bigger graph, right? Just no edges. However, you just cannot have just the edge only without the n vertices. It's just undefined for the edges because you don't have the n vertices, right? So this is okay, but this one here is not, right? All right, good. Okay, so this one is done, okay? Let's talk about connection, okay? Connected, which we kind of did already. And I will want to actually mention one thing here just before I forget. Okay, so one thing you want to also make sure you study and convince yourself whenever we talk about spanning and we talk about connected, they are not exactly the same. But they are somehow related as well. So that's something we'll see today as well. Just remember, they are not the same. But how exactly they are not the same, you want to study and just make sure to summarize the points. But we'll mention that today. Okay, so let's now take a look at connection. Okay, you can definitely look at the definition on the slides, but let me just mention that. Connected graph. What does it really mean for a graph to be connected? Okay. So for a graph to be connected, so let's say we're given, let me just make it a bit smaller. So let's say we're given a graph G, which will be, just with a set of vertices and a set of edges, okay? And if the G here is connected, think about connected as more like a Boolean function, right? Take a graph as input, return true or false. True will be it's connected. False will be it's not connected, let's say. Okay? The G will be connected if and only if something I said earlier. If you pick any two vertices, they are not equal to each other, any distinct vertices, and you're able to find a path between them. In that way, it is connected. Otherwise, it's not connected. Let's formulate this a little bit. For every x and y are vertices, distinct vertices to be more precise. So x is a vertex, y is a vertex. And we don't consider x and x, right? We just consider two different vertices. X not equal to y. And the property here should hold. Okay? So I want to introduce another term, which we kind of saw that last time. X should be reachable from y. Or we can say y is reachable from x. They kind of hold symmetrically. X is reachable from y. Or we can say y is reachable from x. It's okay. Okay? And when we say x is reachable from y, what we're really saying is there is at least one path for you to go from x to y. The path can take an arbitrarily many number of edges as needed. Okay? There is at least a path between, could be multiple paths, that's okay, but at least one, between x and y. And for example, this graph over here is connected. For example, you can see from A to F, one path right here, already done for this pair. Although we got more than one path, right, to actually go from A to F. Doesn't matter, at least one. And if I pick another one, let's say B and D, right? So you can go from here and here, or you can go from here to here, at least one, right, etc. You can definitely pick. If the way to really show it is by choosing all the pair of two vertices from the graph and show that there's a path between them. Okay? Now, another follow-up question. Let's say given a graph. How can I show that the graph is not connected? What should I do?
Find any two vertices that cannot be reached.
Exactly, right? Let's see that logically, right? If you want to disprove about connectivity, not connected, G implies there exists at least one pair of vertices, x and y, right? Similar condition here. So x, let me write it slightly differently. I can say x and y are both vertices, and also x is not equal to y, and then there's no path between x and y, so it's not reachable. X is not reachable from y. Okay? So they're somehow related, right? Exactly logical negation of each other. Okay. Now here comes the important question, all right? Now that we learned about spanning, we learned about connected. Given a graph that's spanning, can we conclude it's also connected? Okay, let's give it a try. Well, let's think about this is like a property. Let's say I state the following property. A spanning graph is also a connected graph. This is the property I'm saying. Now you want to prove or disapprove. If you really hate mathematical induction, you better try to disprove it. But to really disprove it, you want to find a witness. Can you find a witness to show that it's spanning, but it's somehow not connected? Yeah, go ahead. You want to prove it or disprove it? Disprove it, okay? Give me a good idea.
Take a graph with two or more vertices and
Actually, what? Remember it's spanning. You cannot say just two or more vertices. You got to take all the vertices.
No. So for any graph with more than two vertices, spanning some graph without any edge.
Without any edge. Okay, I see what you mean. That's one. Yeah, that's good. Okay, that's definitely one way to go. I agree. So for example here, if I simply take all the vertices Remember, this is already a spanning graph. At the same time, it's not connected, exactly what your fellow student said. So there's a one counterexample, all right? So there's another one. I kind of give a hint. If you don't mind, let's see it, okay? Okay. All right, this one here. Over here, let's say we got all the vertices. Of course, in order to be spanning, first of all, it's going to be spanning but not connected. Well, if you don't take any edges, just not connected. That's something we said earlier already. But let's try. So in order to be not connected, here, 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 here. It's not connected because somehow you can see, oh, actually it is connected, I beg your pardon. Okay, let me be a little bit more conservative, right? Or just one example, okay? You will later see that there's some property about what does, in order for the graph to be connected, there's got to be some condition it has to satisfy. That's something we'll see a little bit more precisely, right? All right. So basically, for this example here, so this is a spanning subgraph. Subgraph that's not connected because there's no edge or no path from F to all other vertices. Right, you can see F here is simply isolated. Okay. All right, that's good. We've got about 2 minutes before halfway. Okay, how about we do this? The next one is somehow also related. We talk about what does it really mean for a subgraph to be connected, right? So let's now talk about something called connected component. Okay. Let's now see the definition here on the notes. Given a graph G, so we can say that there is some connected components. Sometimes the acronym would just be CC, right? Capital C, right? I'm not too sure if that's standard, but at least in this course, whenever you see me write capital C1, capital C2, I'm just trying to label the connected components in the graph. Okay, connected components of some graph G. Okay, so there we go. Here is the definition. Okay, it is a maximal connected subgraph of G. Okay, hang on. I know it's doesn't really say much, right, by the definition. But let's see what maximal here really means. Maximal simply means for this particular connected components, it's simply not possible for me to extend it any further by reaching out to other vertex in the same graph. It's already the maximum possible, right? But we'll see example. No further extension is possible to make a larger connected subgraph. Okay, you can just write it down. We'll see one example, okay, quickly. First of all, larger and connected subgraph. It's just not possible. All right, let's see right away. Here's a graph. First of all, is it connected? No, right? Well, just make sure you convince yourself it's not connected because, for example, this square is completely isolated. Also, this upside down T-like subgraph here is also isolated. Also, this guy here is also isolated. Each one of them is already the maximum in the following sense. This square over here, is it possible for me to build a strictly larger connected subgraph? For example, if I pick this one here, I can make it a larger subgraph, but it's not a larger connected subgraph. Because in order for that larger subgraph to be connected, there's got to be existing some edge like this, but there's no such edge at the moment. So this subgraph over here is already the maximum possible that's connected. All right, so what we say is the following. This one here is connected component number 1. This one here is connected component number 2. And this one here is connected component number 3. One more question before we take a short break, and I'll continue. If I tell you that a graph is connected, what can you say about the number of connected components in the graph? Just one, exactly, right? So let's now revisit very quickly, right? If you go back here and see that. This graph here is connected already. Well, basically, it's not possible for me to extend any further because that's already spanning. It's not possible to extend it any further. So this is just the graph itself. So this is the only connected components we have. So whenever you got a single connected components in the whole graph that's equal to itself, that means the whole graph is connected. That's something we'll see as well once we try to start doing graph traversal. All right, so why don't we take a short break? I still got 1 or 2 more points to make on this example here, but let's take a short break, okay? Let's revisit this example here. First of all, we know before the break, there are 3 connected components there, right? 3. Let me just make it a little bit more formal and a little bit visual to see how you can understand about connected components. And then I'll ask you guys one question, okay? So let's now formulate it a little bit, okay? Between two connected components, they are not the same. For example, I'm talking about CC1 and CC2, for example. They are two different components. What can we say about them? Between each pair of connected components, you can say distinct. Say CC1 and CC2. And we know that they are not the same connected components. All right, so now let's formulate some condition here. Right? What can we say? Well, it's really to do with the maximal property that we talk about. Each connected component is already maximal. So that means if we consider these two, look at this one here and look at this one here. If I pick some arbitrary vertex from each one of them, I pick this vertex here, arbitrary. I pick this vertex here. Are they reachable to each other? No. If they were, these two connected components would have been merged into a larger connected components. It's a very important property about being maximal. Okay, let's write it down. For every x and y, x is a vertex. I could have said CC1 is G1, E1, CC2 is a G2, E2, but let's not bother, right? Just make it a little bit more intuitive for this one here. But we do have some logical operator to help us. It's a vertex in CC1. And y is a vertex in CC2. And then x is not reachable from y. Otherwise, CC1 and CC2 could have been merged into a strictly larger connected components. CC2 could have been merged to a larger connected components, right? It's really to do with every individual connected component is maximum by definition, right? So the maximum here is so important to understand what that really means. All right, let's visualize this a little bit, and I'll ask you guys one question. So basically what you think about, if you got two clouds, the first cloud is for CC1, and the second cloud over here is for CC2. I pick some X from here, I pick some Y from here, and it's simply not possible to have any path between them, simply not possible. Okay. That's simply, if you, and this must hold for every combination of X and Y picked from the two connected components. So here's one question. What would be the minimum number of extensions to make the above graph right here connected? When I say extension, you can add edges, you can add vertices, you pick. But it's got to be the minimum possible. What's the minimum? Sorry, say it again, sorry? Two? You want to add two vertices or two edges? Okay, where exactly do you add it? Just give me some example. Yeah, exactly. I know your point. Thank you so much. Okay. Basically, well, think about it this way. If you somehow want to make the graph connected, you're basically reducing the number of connected components by adding edges. Okay. So think about what we have right now is this. So what we got is we got CC1, we got CC2, and then we got CC3. Right? CC1, CC2, CC3. And pick one from here, and link them. So pick one here and pick one here, link them. So this will reduce the number of connected components to be just two, from 3 to 2. And then I can pick one here, link them. So pick one here. Oh, actually I don't need to, just link them. After these two edges, so now I got only a single connected components that's not connected. All right? Hopefully they kind of make it a little bit better. Okay? All right, let's now go for 3 more terms. Okay. Now we're going to talk about, very related, we're going to talk about forest, tree, and spanning tree. So these are the 3 more. And then hopefully, I'll try to finish that hopefully within 20 minutes, I'm hoping. And then we can do a table. Okay. Next one. Forest, trees, and spanning tree. Okay. They are very related. Okay. Forest is basically a subgraph that's acyclic. Oh, first of all, it's got to be undirected. Okay, and then it's a subgraph. And then, most importantly, no cycle. Or acyclic. Okay? So this is the most important property right here. So let's see just one example for the forest. So let's say I want to have this subgraph here. I want to have A here, B here. Let's say just what happened to be spanning, right? Just happened to be. Right? Here, oh, actually the graph itself, but that's okay. I just want to make it more explicit, right? You can think about this particular graph over here is a forest by itself. It's a graph is itself a subgraph for sure. And also, there's no cycle, right? It's not connected, but that's okay. It's not a requirement to be a forest. And let's see here. Okay, good. Let's talk about being acyclic. Okay, you will see there's one condition there in the slides to say what does it really mean for a graph to be acyclic. Let's talk about that, right? And so be careful. Okay. Okay, so let's now develop a little bit further into this line here about acyclic. Hey guys, at the back, do you think I can close the door at the back? That might be a little bit better, right? It's a little bit too loud outside. Yeah, thank you. Thank you so much. Okay, so let's talk about this no cycle condition, right? So any two vertices are connected by, okay, here we go, at most one. Okay, let's now look at this. This is one condition in order for the graph to be acyclic. Okay, at most one. What's the mathematical formulation for that? Less than one? Less than equal to one, right? Okay, just be sure. Okay, that's important. We're gonna play with it, the condition. Okay, at most one. Right here. That means less than or equal to 1. For example, so here you can see between E and D, simply no path, which is okay. 0 is like a special case for less than or equal to 1. And between A and E over here, there's only one path, but not more than one. And also between A and C, there's only one path, but not more than one. So if you check this for every pair of vertices, you will be able to conclude that it's acyclic. Okay, less than or equal to 1. That's just another way to see the acyclic property. Okay, however, we can talk about the special cases. Okay, so at most one right here. Okay, let me just make it a little bit larger. Okay, at most one. Okay, and I will just put some special case. Okay, I'll put it here. Special case. If there is a pair of vertices U and V that's actually connected by 0 path. This special case will still make it a forest because 0 is less than or equal to 1. You're still satisfying it. For example, here you can see between E and D is simply no path between them, 0. So what can we say about this particular special case for a forest? Well, we just say that the forest is just not connected. All right? So this tells us a forest, that's the forest is not connected. In general, a forest may or may not be connected. May or may not. Right? Let's now highlight it right here. So what's so good? All right, I'm talking about what will be a forest. Let's talk about what if this constraint is violated, meaning that the less than or equal to 1 is violated for some pair of vertices. What will be the negation of less than or equal to 1? Larger than 1? Yeah, larger than 1, greater than 1, or larger than or equal to 2, right? Good. Okay, let's be logical here. Okay. So let's play a little bit further right here about this condition here. Okay. So I'll go further here. What if you can say larger than or equal to 2? Well, of course, equivalently is also larger than 1, right? Just play with it. Larger than or equal to 2, path. Existing between two vertices. What can we conclude? Before we say that, if you can find one pair of vertices where there's zero path between them, we say that the whole graph is not connected. But now I'm saying, if I can find another pair of vertices, however, they are more than 1 or less larger than or equal to 2, edges between them or path between them, what can we say then? There's a cycle, or we can say the graph is not cyclic, right? Very good, but let's now try to see how can you show it? How can you kind of justify it, right? I'll show you some nice visualization. Okay, first of all, that means the forest is cyclic. Oh, I shouldn't say it's not a forest anymore because it's cyclic. I beg your pardon. I should really fix the wording. So this is not a forest anymore because it is cyclic. In order for a subgraph to be a forest, it cannot be cyclic, right? Let's see how we can visually prove this. Very easy, okay? Let's say this. Since we talk about undirected graph, I'm talking about two vertices. Let's say I got x, I got y. And I'm claiming that there are more than, larger than or equal to 2 paths between them. So let's abstract a little bit about how the path should look like. That means from x to y, this could be one path. I kind of use a curly line to say there might be multiple vertices involved in the middle, right? So this will be path number 1. And then, since I say more larger than or equal to 2, there could be another path over here. So now, why is this graph cyclic? Isn't that obvious? Right? Because x following this path, get to y, and then come back using another path. It's a cycle. Right? Okay, so good. So you can think about x followed by path 1, followed by y, followed by path 2. It's a cycle. This kind of like an abstraction mechanism will be so useful whenever you want to prove some general property or algorithm on the graph, right? You want to be able to draw some cloud and think about what you know about each individual cloud, right? Okay. Forest done, and tree. A tree is a forest. However, the extra requirement is the tree must be connected, okay? Tree, right here. It is a connected forest. Now, of course, in order to be a forest, let's remind ourselves, that means undirected, also acyclic. Whether or not it's a spanning, whether or not it's connected, for the forest part, is not our concern. But for now, for tree, we add one extra requirement by being connected. Okay, one thing to say very quickly over here. So this one here is a forest. This graph over here is a forest. But not a tree. Not a tree because is not connected. Right? That's something we kind of went over earlier. Because, for example, between E and D, it's not connected. Right? It's a forest, but it's not a tree. Good. Oh, another one I can just draw very quickly, before I move on. So let's say we got trees over here. It's definitely more specialized kind. So think about we got trees over here, and also we got forest. Oh, sorry. There we go. And that would be forests. And this one here is a forest, but it's not a tree. It's basically a forest that's not connected, right? Not connected. Okay? Let's play with this forest over here. First of all, the way to see a forest would be, because the forest itself is acyclic, right? It cannot contain any cycle. But in this particular case, at the same time, it's not connected. So we can somehow break it down into different connected components, which we just learned, right? So there's something over here. Let's do that first, and then we see how we can create a tree out of this. So this part here. So this part here. Is connected component 1. Maximum, it cannot extend any further. This is connected component number 2. Okay, that's something we know. And we have a special, we can now qualify this a little bit more. So this is a cyclic connected components number 1. And cyclic connected components number 2. So another way to see what a forest is simply a set of acyclic connected components. That's another way to see that. Okay? So I'll put it here. A forest is a collection or set of acyclic connected components. Okay, just another way to interpret. Okay, let's make some tree quickly. Okay. Actually, quite straightforward, but let's just do that. Okay. So let me just copy this diagram here. Okay. Oh, sorry, not here. I think maybe the best way to do this would be, let me see. Okay. Let me copy this one. Okay. I want to show you just one tree. Okay, just one. Okay, just here. Okay, that's a forest we have. However, I just want to look at one of them. So let me just erase this part here. Oh, sorry. Just this part here. Oh, well, we should redraw that. Okay, that's good. And then I just want to get rid of this, and then I'll redraw that. Okay. Oh, sorry. There we go. All right. So this example here, just want to emphasize that a tree itself does not need to be spanning. It does not need to occupy the whole vertex set. So I would say this one here this one here is a tree. A tree that's not spanning. First of all, you can see that this subgraph over here has no cycle. And also, it is connected. You can see from all these nodes, they connected to each other. Not a problem. And also, it's not spanning because we left out D and F from the original graph. Okay, it's a tree. Okay. Questions? All right. Yeah, it could take some time, right, to digest. Okay. Let's now try to do the final one, spanning tree. And then I do have some interesting question. I will be very impressed if somebody can tell me the exact answer. Okay, but let's see, spanning tree. Okay, spanning tree here. What's a spanning tree? By definition, it is a connected spanning subgraph that has no cycle. We will talk about, the different property here, okay? It is a connected spanning subgraph that is acyclic. Another way to say would be it is a spanning subgraph that is also at the same time a tree. So these are just two different from different angles to define the same thing. I would suggest when you study for that, just look up the property for the corresponding terms and see if you're convinced. All right? But let's see here. And then I do have a question for the whole class. Okay? Spanning tree. I want to give you a different example here. Okay? I got 5 here. Okay, we'll just draw. Okay. So here, let's say one subgraph. Let me just say this. Spanning tree number 1, spanning tree number 2, spanning tree number 3, spanning tree number 4, spanning tree number 5. Okay, I'll just give you 5 examples. Okay. Here, here, here. Okay, just wait, bear with me. This, this, this. This, this, this. Let's say the first 3. Given that I have already connected A, B, C, and E, how many more do I need to connect to? 2 more vertices, right, in order to be spanning. So now, but of course, the way you connect, you shouldn't create any cycle. For example, if I say I just put another, maybe between, actually there's no, but you see my point. If you don't want to create any cycle, okay? So there are different ways to really connect to 2 vertices. I just need to connect to F and D. I can connect this way, or I can connect this way, or I can connect this. They're all spanning trees. Okay, just 2 more. And then let's say if I got, let's say here, here, and here. Here, here, and here. I have connected 1, 2, 3, 4 vertices. I need to connect to 2 more, right? I can either connect this way, or I can connect this way. Do you guys recall some relations I said between the number of vertices and number of edges? Okay, so now let's revisit that formula again. I have a question for everybody. Okay, if the subgraph G that we're considering so G is a spanning tree. Implies the number of edges will be exactly the number of vertices minus 1. Okay, let's now just highlight this property here. And in our case, the number of vertices is 1, 2, 3, 4, 5, 6. Number of edges, right? I want to convince you. 1, 2, 3, 4, 5, 6, 7, 8. Right? So, how many edges do we have for each spanning tree? 6 minus 1, 5. One, two, three, four, 5. 1, 2, 3, 4, 5, etc. Here is my question. I just want a number. How many possible spanning trees given this setup? And another thing is, it is important to say this graph here is also connected, right? You can think about the original graph I have, all the vertices, and then I got all the edges over here. The graph itself is connected, right? So now I'm asking, in total, how many spanning trees can I ask you to draw? How many different spanning trees can I ask you to draw? How many? I just want a number. I'll pause for 2 minutes. And I have a hint for everybody. What is that? Huh? Yeah, combination, yes. You're definitely on the right track. Okay, good. Okay, I'll pause for 2 minutes. For those of you who took 2030, not EECS, but Math 2030, you should be able to answer this, or at least get some idea. You definitely want to consider that property to say the number of edges should be the number of vertices minus 1, for sure. And in this particular concrete example, where the graph is connected, and we got 6 vertices, we got 8 edges. And also considering all the examples we have, how many edges do we have in the spanning tree? Right? So that's altogether will be your hints. If you do the corresponding calculation, you should really get a number, integer. And don't really just try to explicitly enumerate all the spanning tree and give me the number, right? That's not the way to go. I can easily give you a much bigger number, right? There's no way you want to manually draw this to see how many possible. Not the way to go. Number. Give me a number.
I was just going to say like 5 factorial, but I'm not sure.
5 factorial? No. Too many. Number.
56.
56. Anybody? Yeah, that's A choose 5. Yes, okay, good, okay. Yeah, I think both of you actually got the right answer, okay? So now here's the thing, okay? It should be, given how many edges we have, we just need 5 to make it a spanning tree, given that the graph is connected. So it's going to be basically 8 edges. And I just want 5. And the 5 here is the number of edges in a spanning tree. Okay? So this is a choose operator. All right? And just this will be turned out to be 56. Okay, first of all. And for your information, okay, whenever you want to do n choose k, it will be n factorial divided by k factorial multiply n minus k factorial. You have 2 choices. You can memorize the formula, and then if I do ask you a question related to this, you can apply the formula. Yes, that's okay. Another way, I'll post a very short video about how this formula was derived and can be understood. I'll post it to you guys. It's optional, but if you really want to understand exactly how this formula should be understood, that can make it a little better, because in the exam, if you forgot about this formula, you can derive it yourself, right? I'll make it available to you. Yeah.
So spanning subgraphs can't have any edges that aren't present in the original graph?
Oh, so it's just about a notation here. Yeah. So here, Yes, it's a subgraph, right? You can choose the edges from there. For example, let's say for this one, I'm really implicitly saying, I'm not taking this edge, I'm not taking this, I'm not taking this.
Right.
They're excluded.
You can't make an edge from like A to F.
Well, as soon as you do that, you'll get a cycle.
Yeah, but I'm saying you can't have any new edges, so if you remove one edge, add a one that isn't in the original graph. That's not what I mean.
I don't quite follow you. Can you say it again?
So if you remove the edge from A to E and E to F, and then just make A to F, that's not a subgraph of community.
So if you remove A to E,
Yep.
and then,
F, and then just go A to F as an example.
okay, this one here,
A to F. No. A to F is not allowed.
that's correct. That's correct. Yeah. Yep. All right. I only got about 1 minute. I would suggest the following. Okay. How about this? I do want to at least get to the table. How about we let you guys also give a try, and I'll give the answer. Maybe give me 2 minutes, please. Okay. So this is what I want you guys to fill out. Summary of terms. Okay. Okay, I'll make it quick. Okay. This is going to be a table over here. And then so far we talk about subgraph. And we talk about spanning subgraph. And also we talk about forest. And also we talk about tree. And finally, we talk about spanning tree. And I want you to, for each one of them, evaluate against these 4 properties that we spoke about. Directed or not, undirected, also acyclic, and also connected, also spanning. Okay, it's more like a question. So for each one of them, if they must be satisfied, put a check. If shouldn't satisfy, put a cross. If may or may not be satisfied, you can put a question mark. All right, so this could be a nice study guide for you over the weekend. All right, thank you so much. I'll see you Thursday, tomorrow.